So for our first example, we have that a study of 200 randomly selected occupants in passenger cars and 250 selected occupants in pickup trucks show that 91% in cars and 83.2% in trucks wear seatbelts. Doesn't seem like enough to me, but hey, whatever. At alpha equals 10%, would we reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and pickup trucks? So, when we're looking at this type of problem, or this type of process, we start much in the same way that we have normally, with those first couple of steps about basically being sure that we're allowed to actually do what we want to. So, for one, just being sure that these things are as we need them to be. There's an implied amount of randomness here, it's stated, and then also these are independent samples. So we want things to be independent here, not dependent for these, because there's no direct connection between the car and truck drivers. There's no necessary connection. They could technically be the same people for the most part, but at the very least, there's 50 more truck drivers or truck occupants than car occupants, passengers, whatever word you want to use for that. So they can't possibly be dependent, which means that we're at least good on that basic verification. And then from there, if we want to get those p-bar and q-bar values that we need, it's pretty straightforward use of those formulas. P-bar here is going to be x1 plus x2, the number of successes in each trial, where in this case you have to be a little bit careful about that because it gives you them as percentages, not as raw numbers. That's something you need to get also if you want to use this with a calculator, which I'll talk about later. But here, that value 91%, you can get that as a number by multiplying 0.91 times that 200 to get that that would end up being approximately 182 people for x1. Then for x2, you take that 83.2, multiply that by 250, and you get something like 208, where rounding is a little bit picky here, so you may get a little off, but just be careful with that. You should get something in that neighborhood. Anyway, once you have those numbers, then you also take N1, N2, so 200 and 250, and you'll get that P-bar is approximately 0.867, so Q-bar, its complement, is going to end up being, I should be a little wavier about that, approximately 0.133. Those are our values for P-bar and Q-bar, and then if we want to be sure that they are large enough, well, we need that. In this case, both are above 200, so we're fine in that regard, as long as these things aren't so incredibly balanced, out of whack, unbalanced. Why I said it that way. As long as, in this case, they're good enough. Like I said, don't usually worry about that too much. Here, we're fine. Anyway, with those in mind, we can talk about our hypotheses and our claim, where here the problem stated a little bit weirdly. Let's remember that what the problem wants is to see if we would reject the claim that the proportion is the same. We're looking to reject the claim that proportion 1 is equal to proportion 2. So we're being a bit led a little more than usual here, but it's the same kind of idea in terms of a claim and the opposite of a claim, which here would be that they are in any way different. We're like normal, because we have an inequality, that's our null hypothesis, and its opposite with strict inequality is the alternative to it, where we are claiming the null. So when we get to our ending in terms of our conclusion, remember that because we are claiming the null, our conclusion is going to have language like we have enough evidence to reject the claim, or we don't have enough evidence to reject the claim. Just a little bit of stickiness with that there. The most important thing, but it is very subtle. Anyway, that's what we're working for our hypotheses. So for our level of significance, remember that's generally going to be given, and it still is here. That's 10%. And to be sure, this is two-tailed. Now, it being two-tailed kind of makes our life a little bit easier because, as I talked about in 8.2 and 8.3, the decision of what's P1 and what's P2, pretty much arbitrary. it can throw off where you end up just a little bit in that same sort of way that you might get flipped around in terms of whether it's left or right-tailed and which one goes where, but here we got two, so we can be a little bit less careful, I guess. We'll see another example when I'm talking about a little bit more, but here we got two-tailed tests, so we can move on to, well, actually performing the test, where if you want to do this using the critical value method for your critical values, what you would get is something like the inverse normal, in particular, plus or minus of inverse normal 0.9501, which is a very classic set of critical values, about plus or minus 1.645. And then from there you get your rejection above the positive one, below the negative one, just like before. Or if you prefer, you can use the p-value approach, which is what I'm going to use, because I'm the teacher and I can do what I want, and also because I still think p-values are better. But just for reference, if you need the critical values, it's the exact same as it has been in any other z-score critical value idea. You're just finding the breakoff points. And the p-value still means exactly the same thing, just looking at it essentially on the other side of the coin. These are two roads to the same location. It's just one finds one thing first, the other goes a different way. Anyway, if you want to find the p-value way, you need to get the z-score. And to get the z-score means using that not very friendly formula. Oh boy. But not the worst thing in the world. So, we are going to have some not very friendly notation though. Here, remember, we've got p-hat 1, p-hat 2. So those would end up being as given. That value 0.91 minus 0.832 for 91% and 83.2%. Then that's going to be subtracted. It's going to have subtracted from it, p1 minus p2, but we're kind of assuming p1 and p2 are the same, so p1 minus p2 should, and for the purposes of our assumptions, will basically always be 0. Just like mu1 minus mu2 was generally always 0. Then we're going to take this and divide it by that standard error type term with a little bit more nastiness for the bars, where we've got p bar and q bar, so that's going to be 0.867 times 0.133, and then that's multiplied by 1 over 200 plus 1 over 250. So not the nicest formula. Again, I don't really care if you memorize it, but just know it's the same flavor of z-score thing we've been talking about with necessary adjustments for this specific context. Importantly, once you get past all of that stuff, you'll end up with a z-score of about 2.42. And when you have that z-score, you can then go on, use the calculator however you want to, whatever gets you to the place that you're there most comfortably, whether it's seeing that critical value and the rejection regions, or the p-value using the calculator, the table, what have you, get your distribution. You'll have a picture like that, which hopefully tells the story that you need to see, but just to be sure, we can get our p-value is approximately 0.0156. So, up to my bad handwriting, about 1.5%, which hopefully we can tell is less than alpha. And because our p-value is less than alpha, and this is fundamentally the same process that we've been doing for the last chapter and a half, we still will reject the null hypothesis. P is less than alpha, doesn't matter whether we're looking at a pair of proportions, a single mean, or even some of the other stuff you might have done in your own time, like testing with standard deviations. If the p-value is small enough, you still reject the null hypothesis. Again, it's a little bit hazy, is a little bit of freedom of movement in terms of how you select that value alpha, assuming you're not just reading a problem, but In this case, 10 is bigger than 1, so we reject HO. And because we reject the null hypothesis, or equivalently, if you want to think about it in terms of these guys, which you probably should have been able to see already, because we are in the rejection region, we could say something to the effect of, we have enough evidence to reject the claim that the proportion of occupants who wear seatbelts is the same for passenger cars and pickup trucks for level of significance alpha equals 10%. Gotta remember that has to be in there somewhere. If you don't always state it, it is what allows you to make that decision. Because if we made alpha 1%, we'd have a different decision. It's a little arbitrary, it's a little bit careful. That's how it always works, though. Anyway, we got one more example for this chapter before we move into our last one of the semester. Hold the tears. Almost there, but not quite there yet. Still got a bit more to go. I'll see you in there first.